Hi everyone, I welcome you all to this lecture series in which now I will be going to start the thermal new chapter, that is thermal properties of matter. So in thermal properties of matter, that is the so let us start this thermal properties of matter. So whenever we say thermal means to say something hot, and we when we say something hot, then it means to say that we are thinking something about heat and rise in temperature. Okay. So thermal properties of matter means to say that we are dealing with the properties of matter that will be going to change when we supply energy to them. Okay. So as the name suggests, thermal properties of matter, properties of matter. So it means we will be going to study the change in properties of material that gets affected by transferring of or by increasing the temperature of the material. So in order to increase the temperature, order to increase the temperature of a material, the temperature of the material, we need to supply energy. So the energy is supplied by transferring when some heat is transferred to the material or some energy. So to increase the temperature of the material, we need to transfer energy to the material. And in order to transfer energy to the material, we need to supply. So there is two ways to transfer energy to the material. That is either direct heating by heat transfer, or by some amount of work. And according to both of that, either heating or work, we will see that both will going to increase the internal energy, internal energy of the material. So this property I will introduce in the thermodynamics. Internal energy is nothing but the energy that the molecules gains and have as having showing some random motion. The thermal properties of matter decides decide how it reacts when it is when any material is subjected to heat fluctuations. Heat fluctuations. Some of the major properties or major thermal properties are that we will be going to discuss as we move along with the lecture. That is heat capacity, thermal expansion, thermal conductivity, thermal stresses. Okay. So basically, we will be discussing here is how heat fluctuations are affecting the material. So to make a feel of it, so consider a solid. So I already discussed that solid is made of some molecules like this. But before going to the solid, let's look at the uh, fluids or gas. Gas. So consider a box that is isolated system, isolated with the surrounding. And we have a diathermal wall. So this wall is diathermal. Diathermal means to say that only only energy is allowed to transfer, is allowed to transfer, but not the mass. Now let's say we have some gas molecules here and we have some gas molecules here. So these are basically a hot one, that is, let's say, at some temperature T1, and these blue ones are cold ones. So that is at temperature T2, such that T1 is greater than T2 at T is equals to 0. Now what happens? So because energy is allowed to transfer through this diathermal wall, so energy is exchanging. So these molecules are transferring heat to this by collision, and so that the heat is transferred from hot molecules to the cold gas. And, and why I'm showing this is to tell you that heat is transferring, heat transfer is happening in the above case, because of because of the temperature gradient or the temperature difference, temperature gradient or the temperature difference between the molecule, between the gas at high temperature to the gas at low temperature. Okay, so we are here having a gas at high temperature, that is T1, such that initially T1 is equal to T2 and energy is allowed to transfer. What happens after sometimes the energy get transferred, and this temperature will be going to rise, and this rise of temperature depends on its thermal properties. So as there is a transfer of heat, I told you that it has its this gas molecules has its own properties to absorb heat, and uh, that will going to change the temperature of these gas molecules. Okay, so that's the concept behind that, why there is a rise in temperature. So when we see there is a rise in temperature, so there is a concept that came, that is thermal expansion. Okay, that is thermal expansion. So thermal expansion can be defined as, in a general way, that when heat is passed through a material to a material, then its shape changes in a way that in a way that that it expands. This expansion this expansion can be in terms of area, length, or volume of the material, because all of these are the defining the shape. If you see some example of thermal expansion are, so in hot summer, the railway tracks often expanded. Railway tracks often expanded. In case of wire, electric wire that is going, that is from where we are getting. So our house is getting electricity. So we know that the resistance is rho L by A. So as the in summer, the resistance in summer resistance will increase. Okay. So these are the examples of thermal expansions. And now we need to understand why there is a thermal expansion in a body, not the reduction. So if you consider the solid, and this solid is having so in the elasticity chapter we have discussed that solid is a form of this kind of a structure. Um, in general, a solid has having a lattice structure, some kind of a lattice structure. You may learn that in chemistry. But here we are considering that these molecules are attached like a spring in a way that these springs are describing the intermolecular forces of interaction between the molecules. These springs are springs showing the intermolecular tubular interaction, intermolecular interactions. And we have shown that the curve that comes out to be for the intermolecular interaction is something like U and R, okay, something like this. And we call this part to be a attraction, and this part is the repulsion. Okay. So let's say this is the potential energy that is stored in the molecule. So at equilibrium, I told you that at equilibrium, the equilibrium distance should be this one, where the energy is minimum. So that is R naught between the two molecules, and that is the energy where it has its minimum. Now, when we increase the heat, what happens? This energy will get increased. This potential energy between the molecules get some energy because of the rise of temperature. And due to that, what happens is the energy will increase. Now the energy, let's say, between the molecules is this. So from minus, let's say for minus 20, it goes to minus 10. So energy get increased. The energy get increased. So now there is a possibility that it get, because when you give energy, so when you increase the energy of the molecules, when you increase the energy of the molecules, only the random motion gets random motion increases. So random motion increases means to say that if it is a mean position, so the molecules will take this solution to that, so they will move closer towards each other, or they will expand. So this R naught will become this, let's say R1, or this become R2, such that R1 is less than R naught and R2 is greater than R naught. So there are two possibilities, either this one or either this one, when you increase the temperature. So if you see that this curve is not symmetric along this R naught, so it means to say that the mean of R1 plus R2 divided by 2 will be come out something here. Okay. So if you say that, okay, so you increase the temperature, uh, you are, so in order to increase the temperature, you give some energy to the molecules. Due to that, there is an increase in random motion of the molecules. That random motion either comes towards each other or goes apart. Both are the possibilities. But anyway, you can say that we need to find a mean of those fluctuations. So if you plot a if you describe the motion of the system, so it will be like some zigzag motion. It will goes towards each other. So the distance will either increase or decrease, but you need to find out the mean. And mean is anyway, if this is uh, if this is the equilibrium distance, if that is r naught, then mean is something apart, something r naught plus some extra that we can call it x. So that distance is actually, let's say, x. So because this curve is not symmetric, that why there is some expansion. Okay. So that's the reason why there is always a expansion. So I can write it in terms of words that why there is only an expansion seen in the object if you increase the temperature. So the reason behind that is that I told you just now that as you increase the temperature of the material, the temperature of the molecules inside the material increases. So as the temperature of the molecules increases, this will lead to, as you as the temperature of the molecules increases, this will lead to increase in the random motion of the molecules. And the motion of the molecules, or you can call it as thermal fluctuations increases. Thermal fluctuations increases, and now the distance between the two molecules, now the distance between the two molecules gets increased compared to its equilibrium distance, which directly leads to an expansion. Okay, so this is the reason why there is a thermal expansion. So when we are talking about expansion, we have three kinds of expansion. So we have linear expansion, we have area or superficial expansion, and we have volumetric expansion. Okay. So as the name suggests, first look at the linear expansion. So the linear expansion is, can we say expansion in the length due to increase in temperature. So let's say if you have a rod, if you have a steel rod that is of length L and temperature T, now you give heat to this rod. Let's say it is at AB. Now you have given a heat to this rod. So this will become, so there is some expansion, that is linear expansion. Now this AB will become B prime. So that is the original length of the rod, and that is the increase in the length of the rod, that is, we can say delta L. So we know that the increase in length of the rod is directly proportional to the change in temperature and initial length. And so we can correlate them as delta L is nothing but alpha L delta T. Okay. Where alpha is the where alpha is the coefficient of linear expansion. Okay. So alpha is delta L upon L delta T, and alpha depends on the temperature of the body. Alpha depends upon the temperature of the body. Yeah, generally we have a alpha of steel that is 1.2 into 10 to the power minus 5 degrees centigrade. Alpha of copper is 1.7 into 10 to the power minus 5. It inverse. Alpha we may define as the increase in length per unit length per unit rise in temperature. Okay. So that is the coefficient of linear expansion. Now let's look at one question on coefficient of linear expansion. So the question is a steel scale calibrated for 20 degrees centigrade is used to measure the length of the rod at 30 degrees centigrade, which comes out to be X. Find the true length of the rod if alpha S is the coefficient of linear expansion. Coefficient of linear expansion is alpha is the coefficient of linear expansion of steel. So you need to find out the true length of the rod, the initial. So we need to find out the true length of the rod. Okay. And we need to tell another question is will, so that is the A part, and B part is will the rod measure the rod, the length of rod longer or shorter. Okay. So try this question. So now try to understand the concept. So if we have a scale, so we have the scale, let's say the markings are something like this 20, 40, 80, 100. So that is calibrated at 20 degrees centigrade. For 20 degrees centigrade, it's correct. Now the temperature at which we are using this is 30 degrees centigrade. So at 30 degrees centigrade, what will happen? This will get expanded. This will get expanded. But the initial and final marking are same. So this expansion will be in all the dimensions, that is 40, 80, something like this. Okay. So at 30 degree, the length of the rod is measured, that is come out to be X. So the length of rod at 30 degree comes out to be X. That is length measured with expanded scale. So for a time being, let's consider that the length of rod is y. So that is the initial length of rod. If you measure it uh, with the scale that is at 20 degrees centigrade. Now rod that we need to understand that the temperature of the rod is not changing. The temperature of rod is already there, but we are measuring that it with this scale, that is expanded scale, and it is giving that x to be its length. So what we need to find out, uh, what is the original length of the rod. So let's find out the expansion in this steel scale. The expansion in this is delta L is alpha L delta T. Okay. If L is the original length of this scale, L is the original length of this scale, then alpha L delta T will be the change in that length. So that is alpha S L delta T. So suppose if it is measuring X with, so that is X is measured with the expanded scale. Expanded scale means now the whatever the units are there. So suppose if it has to measure with this at 20 degrees centigrade, then it will give 20. But if you are measuring it that at here, so that will become 20 plus that expansion, that is 20 plus m. Okay. So x is the length measured with the expanded scale. It's a bit confusing question, but I'm trying to make you understand. Let's read the question again. A steel scale calibrated for 20 degrees centigrade, it used to measure the length of the rods at 30 degrees centigrade. So what happened at 30 degrees centigrade is the length of that scale is expanded. Rod is already there at 30 degrees centigrade, but now the length of the scale is increased. So whatever the unit, if suppose I say that the original length is y, so whatever it gives us, that is y plus delta L, and that is actually x. Okay. So this y is the original length of the rod plus delta L that is there, and that is equals to x. Okay. Am I correct? Okay. So first look at this question. So now I'm just make this rod there. Now you put a scale that is expanded one. So I will make the scale with another color. So this is the scale that is expanded one. So now this is 0, let's say 20, 40, 60, 80, 100, etc. and so on. So let's say we are getting this line to be something 80, or I will put this like this is 80, 80 and 100. This is the expanded one. Original one must be something like this. So that is original one. So that is 0 to 100 here. Now that is 0 to 20, 40, 60. I can put it on another side. So let's say this is the original one. Okay, so this is 100. This is 0. This is 20. This is 40. This is 60. This is 80. And this is 100. So let's say it is measuring this 100. And now, as you expand, it is measuring this length to be 80. So from these diagram, it is very clear that will the rod measure the length of rod longer or shorter? So the scale that is calibrated for a lower temperature, if you take it at higher temperature, then it will measure it shorter. Okay. So first, the correct answer is that if you measure the rod with a scale at higher temperature that is calibrated for lower temperature, then it will then the measure that is given is shorter. Means to say that if you measure the rod at the same temperature that is equal to that calibrated one, and let's say it gives a reading 100 centimeter. Now if you measure this rod again at a higher temperature, then you then the measure it gives is less than that of original length of scale. Okay, so that is there. So the final length that it gives is, so this is not a correct thing. So the final length that is giving is lesser. So it means to say that the initial length is higher, and that is y minus delta L. So that is x. So we need to find y, that is x plus delta L. So that delta L is alpha s L delta T, and L is the initial length of the scale that is not given. So y comes out to be x plus alpha s L delta T. That is this question. Now, that is the fault in metallic scale. That is the example of linear expansion. Now let's look at another question. The question is pendulum based clock. Okay, so I will start from here in the next class. Okay, so that is the concept of pendulum based clock, and what will happen to the time period when the length of the pendulum increases due to the linear expansion. We need to see all these things in the next lecture. Okay.